Hello dear students, this is your SUMA madam. Welcome to the third video lecture on the process scheduling chapter. Today we are just going to learn about the second scheduling algorithm, that is shortest job first scheduling. So as the name itself indicates that this is the shortest job first scheduling algorithm. That is nothing but the scheduling algorithm is always going to select the job or select the process which has the shortest CPU burst time. So that's what the shortest job first. The process with the lesser CPU burst time will be given the chance to use the CPU first. So that's the meaning of shortest job first algorithm. So the SJF algorithm associates with each process the length of its next CPU burst. So in order to work with SJF, each and every process must be aware of its next CPU burst cycle. When the CPU becomes available, it is assigned to the process that has the smallest next CPU burst time. It is nothing but, so every time when you want to just schedule the CPU or given the control of CPU to the processes, we need to select the process which has the smallest next CPU burst time. Say suppose if the processes matches with the CPU burst time, say assume P1 has 3 millisecond, P2 has also 3 milliseconds at that time. So the CPU will be given for the process which has arrived first. Say assume P1 has arrived at 0, P2 has arrived at 1. In this case, CPU will be given for the P1 because it is early arrived. Say suppose in the arrival time, even the arrival time is just going to match. Let us assume this example in which P1, P2 has 3 and 3 millisecond of burst time. They have arrived at equal time. I mean at the time 0, both are available. At this time, simply follow the order of the processes. That is nothing but the process ID. P1, P2. Since P1 is the highest identifier, you have to give the chance for P1. It has two forms. The SJF has two forms. It runs under two forms. The one is that non-preemptive version of SJF, other is that preemptive version of SJF. Non-preemptive, as we all know that once the CPU is given to the process, it cannot be preempted until it completes its CPU burst time. Means, say suppose there are n processes which are arrived at the same time and we need to just choose the process which has the smallest CPU burst time. Once the CPU just given for that process, so other processes has to wait until he completes the job. So once he just releases the CPU will be given for the next process whose burst time is smaller than the remaining processes. So that's what the non-preemptive version. We have the preemptive version in which if the process arrives with the CPU burst length lesser than the remaining time of the currently executing process, you just preempt it. So it is nothing but every point of time you need to just check out, is there any process which is arriving with the smallest CPU burst time than the one which is currently being running? So if so, you need to stop the execution of the process 1 and you have to give the CPU for the newly arrived process. So that's what the preemption. Every point of time, if there is other process arriving with the smallest CPU burst time than the currently running, you need to preempt the CPU. So this scheme is actually known as shortest remaining time first. Shortest remaining time first job or job scheduling algorithm. So shortest remaining time. So you will understand this word when we solve more problem. The remaining time has to be calculated from each of the processes before they preempt the CPU. Now let us just discuss more problems on it. Yes, let us continue with the first problem under the SJF algorithm. So that is the non-preemptive version of SJF. So there are 4 processes, P1, P2, P3, P4. So there are 4 processes, P1, P2, P3, P4. Their arrival time is 0, 0, 0, 0. All are arrived at the same time and their burst time is like this, 6, 4, 1, 5. Okay, so for this we need to run the SJF algorithm, that is non-preemptive version, and calculate the average waiting time and average turnaround time for this algorithm. So in order to show the working of SJF, we are using the Gantt chart so that which process have been scheduled at what time, what's the completion time, what's the waiting time, everything can be easily calculated by this. So as we all know that the Gantt chart always should start with the 0th time, and of course all the processes are ready by that time, so just start scheduling at 0 time only. So since SJF says that the shortest job first, so we need to just choose, because at this time all the processes are ready, we need to just give the CPU for the process which has the shortest CPU burst time among all the 4. So P3 is having the smallest CPU burst time with the 1 millisecond, so that CPU will be given for the P3 first. So P3 is just going to use the CPU for only 1 millisecond, so his job is completed, so CPU is released. Now CPU will be just given to the next shortest CPU burst time. So among 6, 4, 5, the 4 is the shortest CPU time with the P2. So CPU will be given for the process P2. So P2 is just going to start executing on CPU, and he requires only 4 milliseconds. So by 5 milliseconds, he is just going to complete the CPU. After that, so among P1 and P4, P4 is carrying the lesser CPU burst time with the 5, so that the third chance of using the CPU will be given for the P4. So P4 will start running or using the CPU at time 5. Since his burst time is 5, he needs 5 milliseconds to be completed. So at 10 millisecond, the P4 is completing its jobs. Finally, the CPU will be given for the P1 with the burst time 6. So at 10, he starts. At 16, he is just going to complete its job. So this is the Gantt chart according to the SJF algorithm. Now we need to just check what's the average waiting time and the average turnaround time. We all know that the waiting time is nothing but overall waiting time, that the time that has spent in the ready queue. So once it has got arrived, after arrival, how long it could just wait in the ready queue, so that is the waiting time. In order to get that easily, the waiting time could be simply what? The TAT minus the burst time. What is this TAT? This is the turnaround time. What is turnaround time? It is nothing but after he arrived, so how long he took in order to complete its job. So overall completion time minus the arrival time will actually give you a TAT. From this overall time, if you just subtract the actual burst time, this is the actual burst time, that the time spent in using the CPU, right? If you just do minus of that with the overall time spent in the queue or in the system, so that gives the total amount of time he waited for the CPU. That's what the meaning, waiting time. So now let us just calculate the average waiting time. So as we all know that waiting time is nothing but the completion time might be the arrival time at this moment, because we have not yet started with the TAT. So let us just because all have arrived at 0 only. So this is the average waiting time of the P1. So P1 he has started, the first response time of the P1 started at 10 millisecond, but he has arrived at 0. From 0 to 10 he had to wait. So that's what the waiting time of the P1, 10 minus 0. So P2 is arrived at 0, but he got the CPU at 1. So that 1 minus 0 would be the overall waiting time of the P2. Next is that P3. So P3 arrived at 0. He got the CPU at 0 only. So no waiting time for the P3. So 0 minus 0 is the P3. So next P4. P4 have been arrived at 0, but he has waited until 5 millisecond. So the overall waiting time of P4 would be 5 minus 0. 5 minus 0. So 10 minus 0, 1 minus 0, 0 minus 0, 5 minus 0 divided by 4 will give you a average waiting time as 4 millisecond. Next is that turnaround time. So the turnaround time is nothing but what? The overall time it took in order to complete after he arrived at the system. So the P1 is overall completion time on the Gantt chart for the P1 shows at 16. So 16 minus his arrival time, that is 0. So we'll give you a turnaround time of P1. Next is that P2. P2 is completed at 5, but he has arrived at 0. So 5 minus 0, so that is the arrival time of P2. The next is that P3 completed at 1, he has arrived at 0. So that is 1. 1 minus 0 is nothing but P3. Next P4 completing at 10, he has arrived at 0. So 10 minus 0 will give a turnaround time of process P4 divided by 4 will give you a average turnaround time. You can also just substitute this formula here. So TAT, the overall completion time after he arrived. So if you do subtraction between them, you will get the TAT. So completion time of the P1 is at 16 minus 0. Next 5, that is P2. 5 minus 0 will give you a 5. For P3, completing at 1 minus 0 will give you a 1, and the P4 completing at 10 minus 0 will give you a 10. The waiting time, so in the overall time, what is the burst time? If you do only the CPU burst time, will give you the overall waiting time. So that might be, so 16 minus 6 is 10, and 5 minus 4 is 1, 1 minus 1 0, 10 minus 5 5. Either you could follow this or you could just look into the Gantt chart and calculate like this. So overall average and the waiting time of this would be 4 millisecond and 8 millisecond. We'll see the next example in the next video.